In Euclidean geometry, a regular polygon is a polygon that is equiangular and equilateral. Regular polygons may be convex or star. In the limit, a sequence of regular polygons with an increasing number of sides becomes a circle, if the perimeter is fixed, or a regular or apeirogon, if the edge length is fixed. General properties. These properties apply to all regular polygons, whether convex or star. A regular n-sided polygon has rotational symmetry of order n. All vertices of a regular polygon lie on a common circle, i.e., they are concyclic points. That is, a regular polygon is a cyclic polygon, together with the property of equal length sides. This implies that every regular polygon also has an inscribed circle or incircle that is tangent to every side at the midpoint. Thus a regular polygon is a tangential polygon. A regular n-sided polygon can be constructed with compass and straight edge if and only if the odd prime factors of n are distinct Fermat primes. See Constructible Polygon. Symmetry. The symmetry group of an n-sided regular polygon is dihedral group Dn. D2, D3, D4. It consists of the rotations in Cn, together with reflection symmetry in n axes that pass through the center. If n is even, then half of these axes pass through two opposite vertices, and the other half through the midpoint of opposite sides. If n is odd, then all axes pass through a vertex and the midpoint of the opposite side. Regular convex polygons. All regular simple polygons are convex. Those having the same number of sides are also similar. An n-sided convex regular polygon is denoted by its Schläfler symbol, n. For n less than 3 we have two degenerate cases. Monogon, 1. Degenerate in ordinary space. Digon, 2. A double-line segment. Degenerate in ordinary space. In certain contexts all the polygons considered will be regular. In such circumstances it is customary to drop the prefix regular. For instance, all the faces of uniform polyhedra must be regular and the faces will be described simply as triangle, square, pentagon, etc. Angles for a regular convex n-gon. Each interior angle has a measure of degrees, or equivalently degrees, or radians, or full turns, and each exterior angle has a measure of degrees, with the sum of the exterior angles equal to 360 degrees or 2 pi radians or 1 full turn. Diagonals for n greater than 2. The number of diagonals is, i.e., 0, 2, 5, 9. For a triangle, square, pentagon, hexagon, the diagonals divide the polygon into 1, 4, 11, 24 pieces. For a regular n-gon inscribed in a unit radius circle, the product of the distances from a given vertex to all other vertices equals n. Interior points for a regular n-gon, the sum of the perpendicular distances from any interior point to the n size is n times the apothem. This is a generalization of Viviani's theorem for the n equals 3 case. Circumradius. The circumradius r from the center of a regular polygon to one of the vertices is related to the side length s or to the apothem ab I. For constructible polygons, algebraic expressions for these relationships exist. See bicentric polygon #regular polygons. The sum of the perpendiculars from a regular n-gon's vertices to any line tangent to the circumcircle equals n times the circumradius. The sum of the squared distances from the vertices of a regular n-gon to any point on its circumcircle equals 2 near 2, where r is the circumradius. The sum of the squared distances from the midpoints of the sides of a regular n-gon to any point on the circumcircle is 2 near 2, 4, where s is the side length and r is the circumradius. Area. The area A of a convex regular n-sided polygon having side s, circumradius r, apothem a, and perimeter p is given by for regular polygons with side s equals 1, circumradius r equals 1, or apothem a equals 1. This produces the following table. Of all n-gons with a given perimeter, the one with the largest area is regular. Constructible polygon. Some regular polygons are easy to construct with compass and straight edge, other regular polygons are not constructible at all. The ancient Greek mathematicians knew how to construct a regular polygon with 3, 4, or 5 sides, and they knew how to construct a regular polygon with double the number of sides of a given regular polygon. This led to the question being posed: is it possible to construct all regular n-gons with compass and straight edge? If not, which n-gons are constructible and which not? Carl Friedrich Gauss proved the constructibility of the regular 17-gon in 1796. 5 years later, he developed the theory of Gaussian periods in his Disquisitiones Arithmeticae. This theory allowed him to formulate a sufficient condition for the constructibility of regular polygons. A regular n-gon can be constructed with compass and straight edge if n is the product of a power of 2 and any number of distinct Fermat primes. Gauss stated without proof that this condition was also necessary, but never published his proof. A full proof of necessity was given by Pierre Wonzel in 1837. The result is known as the Gauss-Wonzel theorem. Equivalently, a regular n-gon is constructible if and only if the cosine of its common angle is a constructible number, that is, can be written in terms of the 4 basic arithmetic operations and the extraction of square roots. Regular skew polygons. A regular skew polygon in 3 space can be seen as non-planar paths zigzagging between 2 parallel planes, defined as the side edges of a uniform antiprism. All edges and internal angles are equal. More generally, regular skew polygons can be defined in n space. Examples include the Petrie polygons, polygonal paths of edges that divide a regular polytope into 2 halves, and seen as a regular polygon in orthogonal projection. In the infinite limit, regular skew polygons become skew apirogons. Regular star polygons. A non-convex regular polygon is a regular star polygon. The most common example is the pentagram, which has the same vertices as a pentagon, but connects alternating vertices. For an n-sided star polygon, the Schläfli symbol is modified to indicate the density or starriness m of the polygon, as n per meter. If m is 2, for example, then every second point is joined. If m is 3, then every third point is joined. The boundary of the polygon winds around the center m times. The regular stars of up to 12 sides are pentagram 5 halves, heptagram 7 halves and 7 thirds, octagram 8 thirds, enneagram 9 halves and 9 quarters, decagram 10 thirds, hendecagram 11 halves, 11 thirds, 11 quarters and 11 fifths, dodecagram 12 fifths. M and n must be coprime, or the figure will degenerate. The degenerate regular stars of up to 12 sides are square 4 halves, hexagons 6 halves, 6 thirds, octagons 8 halves, 8 quarters, enneagon 9 thirds, decagons 10 halves, 10 quarters and 10 fifths, dodecagons 12 halves, 12 thirds, 12 quarters and 12 sixths. Depending on the precise derivation of the Schläfli symbol, opinions differ as to the nature of the degenerate figure. For example, 6 halves may be treated in either of 2 ways. For much of the 20th century, we have commonly taken a 2 to indicate joining each vertex of a convex 6 to its near neighbors 2 steps away, to obtain the regular compound of 2 triangles, or hexagram. Coxeter clarifies this regular compound with a notation Kp, Kp, Kp for the compound P, K, so the hexagram is represented as 6, 2, 3, 6. More compactly, Coxeter also writes 2, n, 2, like 2, 3, for a hexagram as compound as alternations of regular even-sided polygons, with italics on the leading factor to differentiate it from the coinciding interpretation. Many modern geometers, such as Grunbaum, regard this as incorrect. They take the 2 to indicate moving 2 places around the 6 at each step. obtaining a double-wound triangle that has two vertices superimposed at each corner point and two edges along each line segment. Not only does this fit in better with modern theories of abstract polytopes, but it also more closely copies the way in which Poinsot created his star polygons, by taking a single length of wire and bending it at successive points through the same angle until the figure closed. Duality of regular polygons. All regular polygons are self-dual to congruency, and for odd n they are self-dual to identity. In addition, the regular star figures, being composed of regular polygons, are also self-dual. Regular polygons as faces of polyhedra. A uniform polyhedron has regular polygons as faces, such that for every two vertices there is an isometry mapping one into the other. A quasi-regular polyhedron is a uniform polyhedron which has just two kinds of face alternating around each vertex. A regular polyhedron is a uniform polyhedron which has just one kind of face. The remaining convex polyhedra with regular faces are known as the Johnson solids. A polyhedron having regular triangles as faces is called a deltahedron.